Hey everyone, in this video I'm going to summarize this paper, Fractional Order Finite Time Model Following Control for Uncertain Microgrids Against Time Varying Delay Attacks, so you can fully understand what the researchers did without having to read the whole thing yourself. Let's start with the abstract. This paper proposes a new control strategy to keep microgrids stable, even when their communication signals are hit by cyber attacks that introduce time delays. The method combines fractional order calculus, model following control, and a finite time tracking mechanism, and it's tested both in simulation and on a real hardware setup. Now, let's take a look at the system they are working with. This is a typical microgrid combining solar, wind, a traditional power plant, and energy storage, all coordinated through a central DMS controller over communication links, which is exactly where the cyber attack comes in. Here is the overall procedure of their proposed method, from defining the problem to designing the reference model and the sliding surface, to finally implementing the finite time controller. Now let's see the dynamic model of the microgrid itself, showing how each unit, DSL, storage, wind, solar, connects into the frequency control loop, with the attacker sitting right in the communication path. Let's move to the test conditions. This shows the simulated load variation used to stress test the controller. And here is the resulting imbalance between generation and consumption, combining renewable variability with the load changes. Now this is the simulated variable time delay attack itself. You can see how it distorts a simple sinusoidal signal. Here are the main parameters of the studied microgrid used in all these simulations. Let's look at the control input generated by the proposed controller as it responds to these variations. And here are the tuning parameters used for the controller itself. This shows how the system states converge over time, confirming the stability of the approach. Now let's see the frequency fluctuation result. The controller keeps it within acceptable limits even under the attack. Here is a comparison with other methods: classical SMC, AFT FSMC, and MFO SMC. The proposed method clearly shows better transient response and less fluctuation. This table confirms it numerically. The proposed method has the lowest maximum fluctuation among all compared methods. And here is a broader comparison with other control approaches like fixed time, predefined time, and classical sliding mode control, highlighting the advantages and limitations of each. To validate all this in real time, they built this hardware in the loop tested using Opal-RT. Here is the experimental control input recorded from that real hardware setup. And finally, here is the experimental frequency fluctuation result, confirming that the controller performs just as well on real hardware as it did in simulation. So overall, this paper introduces a robust chatter-free controller that keeps microgrids stable even under cyber attacks that delay control signals, and it proves it both in simulation and on real hardware. I also share some related papers in this field with you. Stay with me.